Hello everyone, and thank you for joining this webinar about Deep Instinct Threat Prevention Evaluation done by SE Labs. I'm Jonathan Kaftan, the VP Marketing for Deep Instinct. Joining me in this session is Simon Edwards, SE Labs CEO. Simon will explain this test, its target, scope of work, type of samples, results, and conclusion. Then Jonathan Gottlieb, Deep Instinct Head of Product, will present Deep Instinct Deep Learning Cybersecurity Solution that was tested. Simon, thank you very much for joining us.
Hi, thank you for having me. Hi, my name's Simon Edwards. I'm the founder and CEO of SE Labs and also the chairman of the Anti-Malware Testing Standards Organization. That's an important fact because we think that when you do testing of security products, you really need to pay a lot of attention to detail and make sure that tests are transparent. We're based in London and we have an experienced team of testers. Generally, we work with not just the people who create the software, companies like Deep Instinct and many, many others, but also their customers as well. And we try and help people make informed buying decisions. We test a range of different kinds of products. This could be endpoint software, such as dclient that we'll talk about today, but network appliances, cloud services, the whole thing. If you do end-to-end full attack chain testing, then you can pretty much test anything. The reason that we test is there's a lot of marketing nonsense out there, claims that are very hard to substantiate, and it must be very frustrating for some tech companies who really do have good products out there when they're all written off as being snake oil. So testing is very important to identify which products do what they say they do and which products don't. Also, it's very expensive to buy these things. So when you're a customer, you don't want to just buy a bunch of different products and hope for the best and test them out yourself. You really want to make sure that your investment in your IT infrastructure is good value for money. Testing realistically is very important. There are lots of reasons why you shouldn't use VirusTotal, and I could probably spend at least half an hour talking about that, but I won't bore you with that for now. What I would say is that if you're testing a product, you should test it the way that it's deployed in real world. That means introducing threats in a realistic way via email or web, not just copying a file across from one desktop to a virtual desktop and then scanning with a product. And you also can't trust that the products do what they say. Now, a detection is fairly straightforward. If Deep Instinct says they've detected a threat, well, then they've probably detected a threat. But they might also claim to protect against the threat as well. They're preventing the threat from doing something bad. And if the threat is quiet and doing things in the background, I mean, ransomware is an example of something that's very noisy. It's very clear when that's doing something bad. But if you have a product or a threat rather that's stealing information, that may be less obvious. And a product like Deep Instinct or Symantec or Kaspersky might say, well, we've prevented that threat from doing the bad thing. But how do you know? Well, the way that we do that is to use forensic level instant response type approaches. We look at what changes were made to the system. You know, did the threat actually run? And if it did, how much did it achieve its goal? And when you're doing this kind of work as well, it's all very well discovering product issues and then giving someone a badge if they do well and giving someone a reprimand if they do poorly. But we want to make things better. So we tell the companies we work with what happened, what went wrong, and potentially even how to fix it. It's very important, that transparency, because if you're reading a test and you don't know what the tester actually did, it's kind of hard to be able to trust the results. Prevalent threats are important because no one really cares about the edge cases unless you're really interested in targeted attacks. In the test we're going to talk about a little bit later in this webinar, we're going to look at some really prevalent and very significant threats, as well as some that have huge impact, but aren't necessarily as prevalent as you might think. For example, you might have ransomware that goes out and affects everybody, or you might have a cyber attack that affects the US presidential election, which indirectly affects an awful lot of people. It just doesn't touch their computers. And there is some skepticism about testing with so-called APTs like this, because you think, well, how can a tester generate the kind of threats that cyber criminals and nation-state actors are generating? Well, actually, there's lots of threat intelligence out there that will help testers make good decisions on that. And ultimately, it's just hacking. There are only so many ways of doing these things. And in fact, even if you have a nation state with the capabilities of doing a whole range of very advanced things, often they won't because there's no need to. I'll give you an example of what an attack looks like from our perspective when a product doesn't work. So in this case, we had a vendor, definitely not Deep Instinct, and probably not one of the main ones you might be thinking of, but still a significant one, and one that was making aggressive marketing claims at the time. And we found a threat that compromised the system, and it did not detect and it did not protect the system. And they said, well, this threat didn't affect the system, so we should be given a pass on it. And what we identified was that the threat added a file to the file system. This file was called server.exe, so not a particularly subtle name for a remote Trojan. And it set the registry so it would run every single time the system was booted. And additionally, it set a firewall rule on the Windows firewall policy that would allow connections into that server. And we were able to see this by monitoring the system and seeing what changes were made. And this is our regular way of doing testing. But also, this still looks a little bit complicated, and some of the people that dispute results aren't necessarily that technical. So what we also do is we will dump the memory from targeted systems so we can show you exactly what's going on. And in this case, what we can see here are the green elements. That's the security product running. The yellow element is our memory dumper, so you can ignore that. And you can see the server.exe file running quite happily. Now I skipped the summary there, so you can just see we have a new file, it's persistent, and it's allowing access. There are other ways that we can check if things have run, but they're not always 100% reliable. We use products like Process Monitor, which are free and everyone can have access to, and that showed that this thing had made over 4,000 different operations. But really, if you want to ram the point home, analyzing memory is quite a useful thing to do. Anyway, here's an example of a targeted attack, such as we used in the Deep Instinct test, and then we're going to get straight on to the results. So generally, certain types of attacks start with a threat like, say, a malicious PDF, which will contain an exploit. And this has to be sent to the target in some way. It might be you persuade someone to download a file from a website, or maybe in this case, you send an email. And maybe the product is able to detect that email coming in and stop it at that point. The issue here is that testers shouldn't assume that products only work in certain ways. If you do the full attack chain, then no matter how crazy an approach you might take to solving the security problem, you have an opportunity to demonstrate that when you're being tested. And here we have another vulnerability in the system, the user. It's not their fault, it's down to training, but they want to do their job. And when they receive this email and they're convinced it's something that they need to open, they will try and open it. And if there are vulnerabilities on their system, you will get an exploit, which looks, in this case, like a raccoon. I'm not entirely sure why, but that's what this animation has got for us. And when that exploit runs, it will download, usually, some kind of payload. Now, at this stage in the attack chain, this is when we would expect a traditional endpoint protection tool to kick in. Often, people claim they can detect the exploits or the act of exploitation. In my experience, that isn't usually what happens. What usually happens is the effect of the exploit is detected, and you would hope that it would be stopped at this stage. But that doesn't always happen. If you're detecting based on hashes, well, that payload is probably completely brand new, even if it's slightly different to the previous ones, and so the hashes won't match, and bad behavior will then potentially occur. And at that point, you might see some of the so-called next-gen endpoint protection products kicking in. They may not be designed to detect hashes. In fact, many are marketed as such. They say, we don't worry about hashes. And at this point, it will detect bad behavior, such as maybe trying to escalate privileges or dumping hashes or pivoting to other systems. Now, you might argue that's kind of a very last minute approach. There are lots of opportunities down that attack chain to stop the threat, but nevertheless, the hope is that the endpoint will ultimately be saved. So that's what we think one example of a targeted attack would look like. Deep Instinct came to us and said, can you test our product? Can you see if we will actually stop threats? We can test ourselves, of course, but vendors can only test what they know, and it's much better to get a third party involved when they have a different way of thinking about things. And what we wanted to know is, could Deep Instinct stop some of the really bad targeted attacks we've seen in the real world over the last few months? And what about things that we create ourselves in the lab? Now, I don't mean that we're going to sit down and just make up some random crazy malware that no one's ever seen before or potentially will ever see. What we did was to act like bad guys have been acting for the last few years, using the very latest sophisticated techniques to generate threats. And we wanted to see what would happen when these brand new things that were unknown at the time of Deep Instinct's development of their product, how could it cope with those brand new threats? And less interestingly, we also had to do false positive testing, because if you create a product that blocks literally everything, you will do very well in a threat test. Unfortunately, your users won't do terribly well when it comes time to do their work. So a good security product has to be able to stop threats and at the same time allow users to be productive and not block legitimate software. We ran this test about a month and a half ago, back in February. But the product that we used had actually been developed, its brain had been trained, its machine learning brain, 6 months previously. So we're not talking about we're finding a threat on the Monday and this thing has seen it the day before and so detects it. We're generating threats after it learnt what threats look like. What we found with the legitimate stuff was 100% accuracy. I mean, that's very good. It's what we would hope to see. And so we're going to move on to talk about the threats. We had different buckets of threats. We had public ones, and this is a mixture of so-called APTs, things that have affected governments, very large industries, and potentially even dissidents from certain countries. These are very targeted, well-resourced campaigns. And then we also have very significant so-called commodity threats. These are ones that are spread throughout the internet, affecting potentially everybody. This could be general ransomware as opposed to ransomware that's targeted at a specific healthcare facility, for example. And then we took targeted attacks. And these aren't targeted attacks that are being sent to the DNC, which is part of the public group. These are ones that we are making in the lab based on three main methods. Fileless attacks, they get a lot of press. Of course, there is always a file involved, but what we really mean is some malware put onto the hard disk. And in these cases, no, they stay in memory. And that can be a bit of a challenge for some security products. Many require the file to hit the hard disk before they can detect and potentially protect. We have Microsoft Office format-based threats. These are things like Word macros or exploits that take advantage of vulnerabilities in Microsoft Word, PowerPoint, Excel, those kind of programs. And we have shellcode injection as well, which is a particularly insidious, nasty way to hack into systems. From the public attacks, as I mentioned, you had the DNC one, you had the US presidential election potentially. We have banking Trojans, botnets, ransomware, and also botnets and ransomware and Trojans that are focused on specific verticals. So like could be healthcare, could be banking, or oil resource companies, that kind of thing. This is an overview of the specific campaigns. So APT 28, APT 29, they were aimed at the US government. And then we have some general banking Trojans. We have some particularly nasty botnets. And what you can see here, we're starting to see some results now. We can see that dClient, Deep Instinct's product, detected each variant. Now, the reason there are different variants is that these campaigns don't just happen on day one and then stop. Generally, what happens is you'll have an attack start at the beginning of some month or other, and over the next few weeks, different variants of the threat will be developed to try and stay ahead of the security companies. Because, of course, if you want to use the word virus, as soon as a virus is known to the world, everyone detects it, and so the developers have to make a new version to try and stay ahead of the game. So for each of these campaigns, we took different versions of the threats as they were generated over the period of that campaign. And we can see that dClient detected each one of those, and in addition, blocked each one. And it's important to remember that a detection doesn't automatically mean a protection. You can detect a threat and let it run quite happily. But in these cases, all of the threats were both detected and stopped from doing what they should. Now, with the targeted attacks, and specifically the script-based ones, we can split those into a further 3 groups. PowerShell Empire is a framework that uses PowerShell that's built into most modern versions of Windows to do all sorts of clever things without there being an executable file put onto the hard disk. VBS malware is a scripting language for Windows, and I'm pretty sure everyone is knowledgeable about JavaScript. What's important to reiterate here is these were threats created in the lab at the time of testing. Now, we don't create PowerShell Empire, but we use PowerShell Empire, for example, to create new threats. And that's exactly what a lot of bad guys do. Most threat reports I've seen in the last year have seen a massive spike in PowerShell threats in the real world. And if that's what's happening in the real world, that's what should happen in the test. Now, these are so-called unknown samples because although we're generating them from tools that are known, the hashes and so on of these files are unique. It'd be mathematically impossible for them not to be, pretty much. And we then additionally used encryption and other evasion techniques to really try and basically get past the product and see if we could trick ourselves onto the system. The Office ones are also split into 3 groups. We have some bad macros, we have some fileless code injection, and there are some vulnerabilities in various Word products that relate to object-linked stuff. So, for example, you might open a Word document and it might pull down an HTA script from the internet and run that. A lot of these things should be patched, but if they're not, you want to know if your security product is going to protect you. Similarly, created in the lab, unknown samples, and we used evasion. And finally, for the targeted attacks, we have shellcode injection. There are a bunch of different methods of doing injection. We use these 4 here: virtual alloc, heap alloc, process injection, and thread hijack. And again, created in the lab, not known or shouldn't have been known, and evasion was used. So despite all of that, these advanced techniques and the attempts to evade detection, all of the historically significant threats were detected. 100% of the DNC and other APT stuff were detected. They were also prevented from executing, and this is an important distinction. You can detect a threat, it might start to run, and you may see some bad behavior, and you might then stop it. But to my way of thinking, you don't really want any bad behavior occurring on the endpoint at all. You want to block that threat from even beginning its journey, because there might be a little bit of damage done. I just don't like the idea of malware running on my system. And in these cases, they were all prevented from executing, which is great. Similarly, with the unknown targeted attacks, they were all completely detected, and in fact, they were all prevented from executing as well. And there were 0 false positives, so it's literally impossible to get a better result in this test. So if you've got any questions, those are my contact details, and I'm now going to hand back to Jonathan.
Thank you, Jonathan and Simon. My name is Jonathan Gottlieb, and I'm the Director of Product Management at Deep Instinct. Deep Instinct solution is an advanced endpoint and mobile protection powered by deep learning. We support both endpoints, servers, and mobile devices with a variety of OS platforms, including Windows, macOS, Android, iOS, and Chrome OS. The clients can fully operate both online and offline while not connecting to the internet, and the management server can be deployed both in the cloud and on-premise. There is no need to rip and replace existing solutions, and the solution can live side by side with them. The solution is autonomous, provides on-device prevention, and has a very small footprint. Deep Instinct is applying deep learning for its predictive threat prevention platform. Artificial intelligence is the industry for tens of years, starting from the 50s, while machine learning, by using various algorithms such as decision tree, random forest, logistic regression, and SVM, are in use from the 80s. Deep learning, which is a unique branch of machine learning, did its real first steps only in this decade. The main difference between machine learning and deep learning is the ability to train models without any need to perform feature engineering. In the case of common domains, such as face recognition, it is needed to bring a domain expert, which will know what are the important attributes to classify between faces, like the color of the eyes or the distance between pupils. Each of them is engineered into a feature, and all those features are fed into the algorithm for training. Deep learning skips that phase, and so it's possible to feed directly the raw data, in this case, the pixels. In cybersecurity, it is the same. Instead of understanding the relevant features to classify benign and malicious files in each file type, for example, specific APIs used in the import table or the entropy of the code section in a binary file, the raw data, in this case, the byte themselves, are being used in the training phase. The difference is reflected into a few interesting differences. The first one, in machine learning, only about 5% of the available data is reflected to the algorithm, comparing to 100% in deep learning. That yields a lower visibility into the data to be trained and afterwards to be tested, making the accuracy to be much lower. The fact that the domain expertise needed for feature engineering makes that process to be longer, and that creates a risk to human mistakes when selecting relevant features. In addition, machine learning models are usually linear ones, which leads to correlation between features to be harder, mostly in problematic domains like cybersecurity. And for last, due to the fact that it takes time to select features, the support on each file type takes time, making many endpoint solutions based on machine learning to support only a limited number of file types. The evaluation testing was done on the latest release of dclient, our endpoint solution for Windows. Our multi-layered solution includes 3 main layers: pre-execution, on-execution, and post-execution. The first layer, the prevention layer, includes 3 engines: deep static analysis of files before they even executed. This is done by deep learning, and the solution supports many different file types, including PE documents like PDF, Office, and RTF, macro scripts, Flash files, Java application, TIFF, and even font files. As the evaluation testing showcased, it provides an amazing detection and prevention rates and a very low false positive rate. The second engine is the dcloud, a file-based reputation service. This acts as a second layer of validation for the deep static analysis. The third layer is the script control to eliminate any fileless script-based attack vector completely. The on-execution layer includes deep behavioral analysis, different behavioral analysis heuristics to catch malicious behavior of processes during their execution, including ransomware and code injection behaviors. And the post-execution layer provides automatic analysis and explanations to the malicious events occurred, and remediation capabilities to mitigate the threat or to take further actions. The multi-layered approach can assist with handling malicious attacks in many of its stages, making chances of success on preventing the attack to be much higher. Take, for example, a banking Trojan campaign, hit by a phishing message in LinkedIn. In this scenario, the victim receives a phishing LinkedIn message that encourages him to open a link to a CV. That CV is a malicious Office file that by using macro, it drops another P file to the file system. Once the victim tries to open this Office file, the file is being scanned by using the deep static analysis, and because it is detected as malicious, it is prevented by the dclient. Even if the Office file runs and the malicious macro script drops another binary file, this P file will be scanned by the deep static analysis as well and will be prevented. In this scenario, once executed, this P file injects malicious code into a remote process to evade detection. Even if the P file executes, once it operates its code injection, it will be detected by the deep behavioral analysis and be terminated automatically before it even injects itself. At the end, different insights are generated for the admin automatically, including classification of the threat, attack timeline, and offline sandboxing that demonstrate what could happen if the files were to run. Also, a secondary remediation action for isolating the device from the network is available for the admin.